Okie dokie. So in this clip, and this is not a long clip, I'll just let you know that in advance. It's not a very long clip. Of course, you could have known that by scrolling to the bottom, but in any case, I want to prove what's called the parallel projection theorem. The parallel projection theorem is going to be our tool to get a ton of similar triangles. Once we're in Euclidean geometry, we can talk about similar triangles. Similar triangles are going to allow us to do a couple of things. They're going to allow us to prove the Pythagorean theorem, which has a zillion proofs, one of which depends on similar triangles. The other thing that similar triangles are going to let us do is talk about trigonometry. So if we're going to talk about those things, we have to have some mechanism to generate similar triangles of various sizes. And so today we deal with this. Let L, M, and N be distinct parallel lines. By the way, as soon as we say something like this, we must be Euclidean. Because as we talked about in previous video clip, if you don't have the Euclidean parallel postulate, then you cannot say L is parallel to M is parallel to N. You don't have that. So the theorem goes something like this. I've got L parallel to M parallel to N. T is a transversal that cuts L, M, and N at A, B, and C, B between A and C, so M is between L and N. T prime is going to be some other transversal that cuts L, M, and N at A prime, B prime, and C prime. The claim is that the ratio between AB and AC, the ratio between red and green, is the same as the ratio between this red and this green. That's the claim. The ratio between the red and the green on T is the ratio between the red and the green on T prime. Okay? So here's what we're going to do. We're going to take segment AC, and we're going to say, let's pretend that AB is to AC. Let's pretend that that fraction is rational. It's some rational number. If that turns out to be not true, if AB over AC turns out to be irrational, then we've got to use some other properties, but that's really sophisticated, and I want to stay unsophisticated for the purposes of this video. So you'll have to read Venema's proof of what happens if AB over AC is irrational. But if AB over AC is rational, we have some work that we can do. And so here's what we do. We basically take AC and we divide it up into Q equal parts. This Q into Q equal parts. So we divvy this up into Q equal parts. I have no idea what Q is, but we divide it into Q equal parts. So this is a 0, this is a Q, this is a sub P. So for each of those little sub-segments, that sub-segment, each AI plus 1 has a length of AC over Q. So what we're going to do is we're going to construct parallel lines to L through each of those little cut points. We're going to construct a whole bunch of parallel lines. Time now for a lemma. We pause for a lemma because what we're about to say needs a lemma. Here's the lemma. Let L, M, and N be distinct parallel lines. Let T be a transversal that cuts L, M, and N at A, B, and C with B between A and C. and T prime is some other transversal that cuts at A prime, B prime, and C prime. If AB is parallel to BC, then A prime is congruent, A prime B prime is congruent to B prime C prime. This is our lemma. And the lemma gets proven in the following way. Let's suppose that T prime is different than T and T prime is not parallel to T. Because if T prime is parallel to T, we're golden. So what we'll do is we'll come over to A prime here and we're going to construct a parallel to T. And it's going to cut over here at B double prime. And then we're going to come over here to B prime and we're going to construct another parallel to T. And it's going to cut over here at C triple prime. So here's my claim. I claim, I have to get rid of these because I don't know these yet. My claim is, because of the parallel construction here, T is parallel to T double prime is parallel to T triple prime, this angle is congruent to that one. Should flow fairly obviously. And this angle is congruent to that one. And since this is a parallelogram, this is congruent to that. And since this is a parallelogram, this is congruent to that. So why does that matter? Because this triangle is now congruent to this triangle. Triangle A prime, B double prime, B prime is congruent to triangle B prime, C triple prime, C prime. Now, why does that matter? Because that means by corresponding parts of congruent triangles, this is congruent to that. And that's what we wanted. So that lemma, now back to our proof, that lemma means that by the lemma, each A prime I plus 1 has length A prime C prime over Q for each I. So when I go to compare A prime B prime to A prime C prime, that's the distance between A prime naught, A prime P, and A prime naught, A prime Q, which is A prime C prime over Q times P over A prime C prime over Q times Q, which is P over Q, which happened to be AB over AC. And since this is congruent to that, I'm done. Well, since that fraction is equal to that other fraction, I am done. We call it parallel projection because we imagine projecting this red segment in the direction of line L and this segment in the direction of line L until their shadows fall on transversal T prime. It allows us to blow things up, and that is helpful to us. It gives us similar triangles all over the place. It allows us to construct, and that's a powerful tool. So that's all I want to say about the parallel projection theorem, but I will say a lot about similar triangles in our next encounter.